All right, welcome back, everybody. Today we are going to be talking about the 6 basic parent functions. Your objective today is that you will be able to identify and graph the 6 basic parent functions. Your notes today are going to start on slide 23, which is probably going to be a little bit before the slides you were working on yesterday or previously. Now, a couple things you want to know. So, what are parent functions? So, parent functions are basically the most basic form of a function. Right? So, the most basic form of a function. We have 6 different ones that we are going to talk about in this class. Our first one is linear, and that's just when y is equal to x. Our second parent function we will discuss are quadratics. That's when y is equal to x squared. Our third parent function are going to be cubics, which is when our input variable x gets cubed. We are also going to discuss absolute values, which is when we take the absolute value of our input. We are going to discuss square roots, and we are also going to discuss cubed roots. And these are going to be kind of the basics as to what are going on. Now, again, these are the parent functions, so these are the most simple forms of these functions. Now, what I mean by that when I say most simple is that after we go through the basic what do the parent functions look like, then you're going to see us kind of start to change them. So what we'll start to do is we'll start to then say, okay, let's put a -3 in front of the absolute value and let's add 7 to the back, and then let's see what happens with that. The -3 and the 7 are going to change what your graph is going to look like slightly, but it's going to have the overall same characteristics of what the parent function looks like. So kind of similar to you and your parents, right? You might look kind of like your mom or like your dad, but you don't look identical to them, right? So that's really what we're going to be discussing here today. So our first parent function, or the most basic one, is our linear one. And again, this is when y is just equal to x. So looking at this, it's really kind of pretty basic to make a table for these. Again, you pick input values, and you simply take those input values and plug each of them into kind of your function up here and see what comes out for y. So if I plug in a -2, since y is just equal to x, I'm going to get out a -2. Similarly for -1, 0, 1, and 2. When I plug those in, if y is equal to x, then those two pieces need to be the same. Now, essentially at this point, we've created a list of points that this function is going to pass through. -0 is not a thing, so we'll cross that off. But looking at these points, -2 is a spot this function will hit. It also will hit -1, -1, 0, 0, 1, 1, and 2, 2. And from there, we can really kind of sketch what the picture of this is going to look like. So let me see if I can get a straight line here. There we go. So we will see that our line is really just a straight line. And you maybe picked up on this already or have seen this before. Since we don't see a slope in front of that x, we can just put a 1 and we could say a 0. And this maybe makes more sense if you think about it in that slope-intercept form. Talking about absolute value functions, so again, this is when y is equal to the absolute value of x. It's important to remember that the absolute value function makes a number positive. Now, what I didn't say there is I don't say that it changes the sign. It only makes it positive. So what I mean by that is if I were to plug in a -2 into my absolute value function, since -2 is negative, the absolute value makes it positive. If I were to plug in a -1, it will make it positive. Now 0 is still 0, but this is where it gets kind of interesting. If I plug a +1 into it, the absolute value does not make it negative, right? The absolute value does not just simply change the sign. It only makes negative numbers positive, and if a positive number goes in, it just stays positive. So this will still be 1, 1. And if I were to plug in a 2 into this thing, a positive 2, then a positive 2 would come out. It wouldn't get changed because it wasn't negative. Now, what does that mean for my graph? Well, it means I'll have points at -2, positive 2, -1, 1, 0, 0, 1, 1, and 2, 2. And from there, I can sketch the rest of my function. And what I'll find about my absolute value function is it really starts to look like a V. Now, on all of our graphs today, excluding the linear one's kind of just so basic that it's hard to wrap our brains around. But with everything else we're going to be talking about today, there's going to be something that we call a locator point. And the locator point for this absolute value function is really located right there. It's where those two lines come to a point. Now, what the locator point is going to do is that's going to be kind of helpful to us in how we actually graph these functions. Looking at our quadratic function, so again, y is equal to x squared. So we can plug in a -2, -1, 0, 1, 2. And to plug in those values, if I take -2 and I square that, -2 squared is going to give us a positive 4. -1 times -1 is a positive 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. So looking at the graph of this, -2, 4 will give us a point here. -1, 1 gives us a point here. Then we get 0, 0, 1, 1, and 2, 4. And we start to see this shape that looks a little bit more like, I don't know, some people like to call it like a U almost, but it's a parabola. So again, we get this graph. Our locator point for this one is actually going to be at the same spot. It's kind of at the vertex of that. So this again is our locator point. And that will be helpful to us as we start to look at more complex versions of these. The cubic is probably the first one of these you've maybe never seen the graph or never realized that you are graphing a cubic. But anytime you are graphing a cubic, it is y is equal to x to the third power. So again, we can plug in -2, -1, 0, 1, 2. If you cubed -2, meaning you take -2 times -2 times -2, you will in fact get a -8. If you cube a -1, it will be a -1. 0 cubed is 0. 1 to the third is 1. And 2 to the third is 8. So looking at our cubic function here now, -2, -8 will be our first one. -1, -1 is our second. Then we get 0, 0, 1, 1, and 2, 8. So looking at these and kind of connecting the dots, our function comes up. It comes through here. It does this little twist move. And then it kind of keeps going up. This is what a cubic function looks like. Now, our locator point on this one is actually going to be this point kind of right in the center here. And again, that's just helpful for when we start to move and graph these shortly here. The last two functions we are going to talk about are the square root function and the cube root function. Now, to look at the square root function, this is where we got to think a little bit in terms of our inputs. So for our cubed root function, y is equal to the square root of x. What we know is that there's only certain numbers that when we plug them into the cubed root, that we will get a nice number out. So we need to be careful in picking our inputs for this. So the inputs we are going to choose are going to be numbers that we know how to take the square root of them. The first one is 0, right? Because the square root of 0 is 0. The second number we are going to pick to plug in is 1. Because if I take 1 and I take the square root of it, the square root of 1 is in fact 1. Now after that, the next nice number that we can take the square root of is 4. So the square root of 4 is 2. From there, we get 9, which we get 3. And then last we would get 16 and 4, but that won't fit on our graph. So that won't be too helpful for us to graph. Now graphing the points we can see, 0, 0, 1, 1, and then 4, 2 shows up, and then 9, 3 shows up right here. So we can see a sketch of our square root function. Now, it is important to realize here that the domain of your square root function is really 0 to infinity. Negative values don't play a role in your square root function because we can't take the square root of a negative number. Now, when we get to the cube root function, this would be y is equal to the cubed root of x. So thinking about this, we can take the cube root of negative numbers, right? So the domain of our cubed root will in fact be all real numbers, which is different than what we were seeing in our domain for our square root, right? Cubed root, you can take the cubed root of a negative number, so that's not an issue. Now, again, when you are working with a cubed root, you really need to think about which numbers do you know the cubed root of them quickly and efficiently. And negative 8 is one, negative 1 is another, 0, 1, and 8 are kind of those nice numbers for us here. The cubed root of a negative 8 will end up just being a negative 2. That's the number that times itself 3 times equals that. Remember, as we were breaking down radicals previously, if you had a negative 8, you could break this down into 2 and 4, which is 2 and 2. So since you have 3 2's, you can pull those to the outside, and since it was negative, pull that 2. This would have been a negative 2 as that simplified answer. So that is another way of just kind of by hand what we're thinking here. Negative 1, the cubed root of a negative 1 is in fact negative 1. The cubed root of 0 is 0. The cubed root of 1 is 1, and the cubed root of 8 is 2. So looking at this, what does our graph look like? We will have negative 8, negative 2, negative 1, 1, 0, 0, 1, 1, and 8, 2. So looking at our graph, it kind of looks like it actually has part of that square root function in it, and then it actually has this other half of it going the other direction. Right, and again, that's because of the fact we can take the square root, the cubed root of a negative number that we get that other half. Now, just like we were saying before, for your locator points, your locator point for your cube function, or your cube root function, will be right there, and for your square root function, will be right there. So again, these are your locator points. So now what I want to do, we're actually going to kind of skip this next slide here. We've kind of talked about that already, so I'm not too worried about it. But I want to start to talk about naming and sketching the parent function. So looking at this, now we start to see some more complex versions of those parent functions. But we should still be able to look at each of those equations and see and be able to relate that back to its parent. So what I mean by that is this. If I look at this first one, I can see pretty clearly that there is a square root in there. And what that means is that the parent function of this whole function must be the square root. Right, so you've identified the parent function right now, right off the bat. And in fact, we do know what the parent function is going to look like if we sketch a graph. Right, the parent function, you can go back a slide if you needed to see this, of any square root is going to basically look like this. This is just a sketch. It's not perfect by any means. Now, the question becomes, well, what does this plus 2 really do to the graph? And for that, or to look at that, I want to go and switch apps here and look at Desmos. So Desmos is just a graphing app, and I've went through and actually put in all the graphs that we were going to be talking about today. And I want to just primarily look at these graphs through the lens of what does adding a number in certain places do to actually affect it. So the one we're looking at right now is actually the square root. So here is our normal square root graph. Let me see if I can get that a little nicer. It seems like we're just twisted a little bit. There we go. Now we're getting better. Nope, don't want that. Okay, so here is that square root function that we were talking about earlier. And what I've done is I've went through and put in sliders, right? So if we move and play with that k value at the end, that's the piece that in our function we have it as a +2 right now. If I make that into a +2, what I see is that my graph really just actually shifts up. And that's really what this k value does, is this k value, if I add something at the very end of my function, it really just moves your function up or down. So then the question says, well, what if I would have added something on the inside of the square root? And if you add something on the inside, you see that it just moves your graph left or right. So inside of your function moves your graph left or right. If it happens on the outside, it's going to move your graph up or down. So that's the square root function. But like, you should really start thinking to yourself, well, what happens if I did that on a different function that wasn't the square root? Like, what if I did it on a quadratic? So if here's your base quadratic, what we just saw before is that, well, if it's on the inside, and I can see that a is on the inside of the parentheses with x there, what we were seeing before is that that piece moved it left or right. So if I actually just try to slide it here, again, I see that that a value, the value that's kind of on the inside of it all, does in fact move your graph left or right. Whereas the b value on the outside still moves my graph up and down, right? So one of them just moves it up and down, that's our outside number, whereas the inside number just moves our graph either to the left or to the right. Looking at our cubic function, right? So our cubic function looked like this. Remember, our locator point was that point at 0, 0. And if it's inside, so our c value here should be what moves us left or right, and that is what we see. Whereas our d value on the outside is going to move us up or down. Okay, so again, if it's happening on the inside, it's moving you left or right. If it's happening on the outside, it's going to move your graph up or down. Looking at your absolute value function, again, this was the one that looks like a V. If it happens on the inside, like I do see with my G there, right, it's the absolute value of X plus G, that's going to be indicative of if it moves left or right. Whereas if it happens on the outside, that will tell us if our graph moved up or down. We've already looked at the square root, the cubed root. We should just verify that the same thing happens here. So let me turn that one off. So in our cubed root function, again, on the inside, the L is on the inside with X. If I move it, this is moving my graph left and right now. And if I adjust M, which is on the outside, that just slides my graph up or down. Now, how do we use that with what we are talking about here, right? So couple of things we want to look for. So when we are looking at these functions, one of the things we're going to be discussing is the actual transformations of them. So what we want to look for is we want to look for vertical shifts and horizontal shifts. Remember that the horizontal shifts are going to happen inside, whereas the vertical shifts are going to happen outside. And what I mean by that is this. Inside the square root here is simply just x. There was nothing happening inside of this one. This 2, however, gets added on the outside of the number, which means this is going to be a vertical shift. Now, when I'm dealing with vertical shifts, if it is +2, it simply means that my graph is going to be shifted up 2. And when I say shifted, we talk about the locator point. So the locator point on our normal standard square root function is just this kind of endpoint of the tail. So what's going to happen is our graph is simply going to move up 1, 2 units. So our new graph is really going to start right there. And then this 4/3 actually has a big range of what's going on in our problem, but that's easier to see when we graph it in more detail. So we will talk about that a little bit more, but I just want to sit there and be able to point this out that this will be our new locator point. And we will dig into these graphs a little bit more here in just a minute. So as we go through, we're going to be looking for vertical shifts. Those are those numbers that are added or subtracted on the outside. And we're also going to look for horizontal shifts. So looking at our next function down here, this one, we can see that we have something that is being cubed. So if we have something that is being cubed, this is going to be known as a cubic function. Immediately, when you know that you have a cubic function, again, you can go back to your graph, but you know your cubic function basically is going to look something along the lines of this, with our locator point being located right there at the center. Now, since we have a couple different things going on, we have this -8, so our graph is actually going to be shifted down 8 units due to this piece, and then we have this +1 that is going on. Now, this is where I hope you're watching the video where you're slowing it down and you're thinking about it. Anytime you are doing this and you have this inside number, what you need to know about this inside number is that this guy lies to you. This guy lies. This guy on the outside always tells you the truth. That is not how you spell truth. T-R-U-T-H. The guy on the outside tells you the truth, but the guy on the inside always lies to you. So if you think that +1 would move you 1 to the right, that's the guy that's actually lying to you. And what you're going to do is you're going to move 1 unit to the left. So what's going to happen with our graph here is that our whole graph is going to kind of change positions. It's going to now be located down 8 units, 1, 2, 3, 4, 5, 6, 7, 8, and it's going to be located 1 unit to the left. So 1 unit to the left means that my locator point has essentially relocated, and my new locator point is going to be there. Right, so first identifying where our locator point is going to be one of the more important things for us to consider. Looking at our next one, our next function, in our next function we can see that we have a cubed root going on. Since we have a cubed root, we can just literally write cube root. And then we just want to look for any basic changes. Again, if there's anything happening out front, don't worry about it. We'll talk about that as we get into a little bit more depth, which is why we didn't talk about any of those pieces. What I just want you to look for right now is there anything added on the back or inside, like on the outside or on the inside? So this guy had a +5, so we know our new graph will be shifted up 5. So looking at this, we'll come over here. Our cube root function typically looked like this. And we had that locator point that was kind of smack dab in the middle. Now, since we do have this +5, we know our graph is going to be shifted up 5. So our new locator point will be right there, just like it was right there on the other one. Right, so finding that locator point is going to be our first start in actually trying to graph the function. And again, we just don't have graph paper here, otherwise we could go into that in more depth, but we will momentarily. Looking at the next one, we see we have something raised to the 3rd power, which makes this a cubic. Remember, all cubics have this general shape to them. Maybe a poor drawing, but you get the picture. The locator point for a normal cubic is right in the middle. So looking at our graph here, this +10, he's the guy that tells you the truth, so you know your graph will be shifted up 10. And this -1, he is the guy that lies to you, so if he is showing you 1 to the left, it looks like you better really go 1 to the right. So our new locator point will be just shifted 1 to the right, and it will be up 10. So our new locator point will be somewhere over there. And again, this 2, we're not just forgetting about it. It definitely matters, but we're not discussing it right at this moment. Looking at the next one, in this next one, we can see that we have a cubed root going on. Remember, if you have a cubed root function, it basically looks like this S. Now, again, looking at some of those clues as to what's changed, If I have a minus 7 on the end, that means we are going to be going down 7. And if I have a plus 5 on the inside, remember, the inside guy lies to you. So plus 5 would make you think that you are going to the right, so we actually go to the left. So left 5 and down 7 means our new locator point will end up down here. And really, the reason I talk about that locator point is when we're actually trying to graph it, that is the idea, or that's kind of our starting point for our function. Looking at the next one, this next one is going to be an absolute value because we see an absolute value right there. Now, on the outside of it, we do have a plus 1, so our graph will be shifted up 1. There's nothing inside the absolute value that has been added or subtracted, so there is no movement left or right, just simply up and down. So if our parent function looks like this, remember our locator point's right at 0, 0. So our new locator point will simply just be shifted up 1 unit from that. Again, we have another absolute value. Nothing happening inside. This one is just shifted up 2. So our normal graph, or the parent function sketch, that did not work out, will look like this. And since our locator point is being moved up 2 means our new locator point will be sitting right there. And that's really it at the moment. So going to the next one, we have our cube root. Because of this cube root symbol, looking at this one, since there's nothing that's added to the end or inside that has been added, there really is no movement in where our locator point actually is. So our locator point for this one is just going to stay put. It's staying right there in the middle. Moving on to the next one. Since we have something that is being squared, we know that this will be a quadratic. Remember, quadratics are the ones that look like a parabola. So our normal parabola looks something like this. This is just our quick sketch with our locator point being right there. And since we see a plus 1, that means we will be going up 1. And since we had a minus 3 on the inside, remember, a minus on the inside, that guy lies to you. You really want to go to the right 3. So to the right 3 and up 1 means our new locator point will be sitting over there. Last slide of these. Here we go. So looking at this one, we have something cubed, so we know this is a cubic. If that is being cubed, then our parent function for that will look like this. And remember, our original locator point starts out at 0, 0. Now, the plus 4 is going to move our graph up 4. And the plus 5 happening inside of what's being cubed, which means he's the one that will lie to you, so we are going to shift our graph 5 to the left. So if I go 5 to the left and up 4, my new locator point will be sitting over there. Moving on to the next one, again, we see we have another absolute value. So we will be talking about our V shape here. So if this was our normal absolute value, then the plus 2 is simply going to move our graph up 2. And since there's nothing happening inside, there is no shift left or right, so our graph will move up 2, and that's where our new locator point will begin. And finally, we come over here to the cube root. For that cube root, again, our parent function looks like this S. Normal locator point is sitting right at the origin. And since we don't have anything that has been added to the outside or to the inside, our new locator point is actually going to sit at that exact same spot. This is really part one, ladies and gentlemen, being able to identify what the parent function looks like, along with what transformations are happening and where that new locator point is being moved to is very important in the graphing process. In the next video, I will walk you through just 3 problems, and then that will conclude your learning for the day. So please make sure you watch the next video. That one's going to be absolutely critical to actually graphing these. Thank you. See you in the next video.